So, this is an organic molecule, and we call it an organic molecule because most of the skeletal atoms are carbon. It's got some nitrogen, it's got some oxygen, it's got hydrogen. Most organic molecules, pretty much every organic molecule is going to have some hydrogen. Some terminology. The atoms that are not C and H are called heteroatoms. So nitrogen and oxygen in this case. And again, I start with water for a lot of reasons. It's an incredibly important molecule. It's a really funky molecule. But it's one that you have some, like not academic contact with. You have like real contact. You have touched water today. I hope. Okay, so the organic bits here, how to dive into this? Let's just do the molecular formula. Anybody got one they want to throw out? It's a lot for the first day. I know it's the second day, but it's your first day. So, molecular formula always, in organic chemistry, always going to start with a C. You put the C first and the H second. And then you put in the heteroatoms in alphabetical order. All right, so N2O, you should not miss that. All right, the heteroatoms in a bond line organic molecule have to be drawn. So you may be looking at this and you're like, C1. I don't know if anybody did. You don't have to tell me if you did. But if you looked at this and you said there's one carbon atom, you're wrong. It's understandable. There's one C on the board though, right? So the way these bond lines work is anywhere there's a bend in the line, or if there were an end of the line, right? So there are 5 carbons in what I just drew, this blue thing right here. All right? The end of a line is a carbon, a bend or an intersection in the line is a carbon. And the reason we do this is there are organic molecules with, hundreds of carbons. It's tedious to write C all the time. So we're going to assume that any atom that's not explicitly drawn is either a carbon or a hydrogen. So bend in a line is a carbon, and then we assume that that carbon has enough hydrogens on it to make 4 bonds. Again, think about the octet rule. A neutral carbon will make 4 bonds. Okay, so carbon. I have drawn 1. You can always write a C if you want. Totally fine. If you write that C, though, you no longer assume it's got hydrogens or anything else. You have to show everything that's attached to it. So now we've got 1. Let's number this. So 1. I forgot about this. 1, 2, 3, 4, 5, 6, 7, 8, 9. Just a little word of advice, write stuff down. Okay, there's this pervasive idea in academia, in popular entertainment, that if you're smart, you can just kind of lean back and figure everything out. And you can't do that. I don't mean you personally can't do that, though I also mean you personally can't do that, all right? Complicated, maybe you can do this, but at some point you're going to run into complicated enough stuff and you can't just figure it out in your head. Get used to writing stuff down, and then you don't make simple mistakes. Okay, so the carbon I've drawn there is 1. This intersection is 2. This one 3, 4, 5, 6. So 9 carbons. And again, CH4 is methane. CO2, if you know the structure of CO2, it's an important molecule, organic byproduct of life. 4 bonds in those things. So anchor 4 bonds in there somehow. You guys should, if you look at a carbon and it's got 4 bonds, it's neutral. If it's got 4 bonds, it will never have a lone pair. So can carbon have 3 bonds? Some early energetic shakes, no, and then some thought. A carbon can have 3 bonds. So the octet rule says an atom can't have more than 8 electrons. It can have less. But a carbon with 3 bonds is going to be really reactive. So it's either going to be a radical, that means it has a single electron, like an unpaired electron, and those molecules tend to be quite reactive, or that carbon with 3 bonds will have a charge. It's got a lone pair, it would be -1. It's got no lone pair, it would be +1. Right? And it's going to do something else after that. All right? So the carbon that makes up most organic matter is neutral. A neutral carbon, a stable carbon, has 4 bonds. All right, so knowing that, how many hydrogen atoms do you think are in carbon 1? 0. There are 4 bonds shown for that carbon. 1, 2, 3, 4. There are only 2 things attached to it. There are 4 bonds. The other thing is, doing this properly, if I write C, I have to write the H, if there's one there. So what about carbon 2? How many hydrogens? Still 0, right? So 1 bond, 2 bond, 3, 4. Carbon 3. 1. There's 1 hydrogen on carbon 3. So let's say then, I, for whatever reason, wrote a C there. Right? If I draw that C, I have to write the H. Like that is incomplete. So if you write the C, you got to fill out the hydrogens attached to it. How many hydrogens on carbon 4? Right. So 1 bond, 2 bond, 3 bonds shown to carbon 4. There's no charge shown to carbon 4, so it's got to have 4 bonds. That means there's a hydrogen here. And if you go around and do this, then each one of the ring carbons that doesn't have something else shown to it has 1 hydrogen. There's a hydrogen shown on the nitrogen and a hydrogen shown on the oxygen. Are there any other hydrogens? Where are they? How many on 8? How many on 9? 2. Yeah. So, right, carbon 8 here, 1 bond shown to nitrogen, 1 bond shown to carbon 9. That's 2 bonds. It's got to have 4. So there's got to be 2 hydrogens there. Same thing for carbon 9. It's always fine to draw those hydrogens in. So you can always write C if you want. You can always draw the hydrogens in. You can just draw 1 hydrogen in. I'm going to do that a lot when we start talking about chemical reactions where bonds form and break. Like I may draw in just 1 hydrogen, and the reason I draw it in is it's going to do something. Okay, so then you count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Everybody get 10? So, seriously, I say this, I don't mean to insult anyone, because I screw this up myself. Counting isn't easy. Counting's actually trivial, right? You've been able to count since a very young age. But if you try to count while you're doing something else, right? If I asked you to count to 100, and then, I don't know, start doing something crazy, banging a pot, yelling at you, cursing at you, drawing flowers on the board, anything that distracted you, you might lose count. You've probably experienced this. They do this in drunk tests all the time, right? So to count, you've got to focus. So, like I said, I get asked a lot, what can I do to prepare for this class? Work problems. So now I'm going to throw in a little, work as many problems as you can. The way I'm going to grade this class is by having you work chemistry problems. So if you read the text and you think you really understand it, you think I'm just not getting at your knowledge, maybe that's true. The way I'm trying to get to your knowledge, though, is by working problems. So if you're not working problems and getting correct answers in practice, your exams and quizzes may suffer. The other thing is to focus. Don't take things for granted. Write stuff down. So if you have time to work out this molecular formula, write it all down. You got to count to 10. All of you should be able to do that. But I promise, at some point in your college career, you will screw that up. Right? It's not because you're dumb. It's because you're human, and humans, this whole thing about focus, like humans actually have trouble with this. If you know anyone who's in the military, a lot of training is to just stand at a post. Like, you have to be trained to do that, because otherwise you will just daydream. How many of you have daydreamed so far in this class? You can admit it. I'm teaching the class. I have daydreams. All right? So, like, here, draw, come up with a molecular formula, and I start thinking about what I'm doing. So it's natural to do that. So work on your focus. Okay. How many lone pairs are in this molecule? Got one. Verbal for a few people. It's like the fourth quarter of a football game. All right. So I'm going to draw the lone pairs in. One on the nitrogen, another one on the nitrogen, two on the oxygen. So again, I'm saying you need to be able to see this at a glance. I started with water. All of you know what oxygen looks like in a molecule. It's got 2 bonds, 2 lone pairs if it's neutral. This next question, any formal charge? That's kind of a trick question. Again, probably very, very soon, I'm going to draw molecules for you and ask you what the formal charge is. I won't show the formal charge. The assumption there is, though, if I don't show you the formal charges that exist, I have to show you every atom and every lone pair. That's the only way to answer that. When you just draw a molecule to talk about it, you have to show explicitly any formal charges. I didn't show any. That means they're all neutral. It means this oxygen's neutral. So 2 bonds, 2 lone pairs. So I've drawn methane. The other molecule you need to know that you probably know almost as well. Well, maybe you don't. Hopefully you don't have a lot of personal interaction with ammonia. It's a strong base, smelling salt. But you've seen it in Gen Chem. Right? NH3 is a base. The nitrogen has 3 bonds and a lone pair. So a neutral nitrogen, 3 bonds, and a lone pair. The conjugate acid of ammonia is NH4 plus, ammonium. Ammonium is just like hydronium. The formal charge is on nitrogen, but the chemical charge is on the hydrogens. Right? So NH4 plus reacts like an H plus source, not like an N plus source. So if you see a nitrogen with 4 bonds, it's going to be positive. If you see a nitrogen with 3 bonds and a lone pair, it's going to be neutral. Or if you see a neutral nitrogen, it's going to have 3 bonds and a lone pair. What else was I going to say here? Oh, the other thing that's really important in these bond line structures any hydrogen on a heteroatom has to be explicitly drawn. So if you write N or O, and there's an H on it, you have to write NH, OH, NH2, bond to an H. If you just write an O out there that's dangling, it's an incorrect structure. We'll come back to hybridization in just a second. This molecule is getting a little cluttered. I'm gonna clean it up. the lone pairs in for now. Pretty soon I'll stop drawing these, but I want you guys thinking about them. Would this molecule be soluble in water?
Yeah.
I like the confidence. Anybody else?
Yes.
I think so too.
All right. Why?
Got 2 hydrogen bonds.
Hydrogen bonds, exactly. So, no, I can leave that. So a hydrogen bond is a really strong intermolecular interaction. It's going to be between a strongly partial plus H and an O or an N, sometimes an S. Something's got a negative charge or a partial negative. Something's got a lone pair of electrons. And like I said earlier that water is a funky molecule. Boiling point increases with molecular size. So this is just something to keep in mind. I'm going to write the technical, all right? So boiling point, all else being equal, increases with increasing molecular size, surface area of the molecule. You can basically sub in for that molecular weight. Higher the molecular weight, the higher the boiling point. This molecule is hexane. It looks like a zigzag line. Hexane has 6 carbons. Hex 6, right? An alkane is just a hydrocarbon. This is called N-hexane because it's just 6 carbons in a line. There are isomers we can talk about. Hexane, what do you think the boiling point of hexane is? Anybody got a guess? That's a hell of a guess, huh? See people instinctively reaching for their phones.
15 Celsius.
15 Celsius. All right. You have a car?
No.
You ever pump gas?
I have.
What do you think the boiling point of gasoline is?
I'm not sure.
Yeah. But, like I said, I'm asking for way precise information.
Probably really high.
It's not really high. It's higher than, so you've all heard of octane. Gasoline is not a pure substance, so it's a bunch of different things, but octane and octane isomers is one of the main components. And the boiling point's in like the 90-degree range. I honestly don't know the boiling point of gasoline. But it's volatile, right? If you spill it on the ground, it evaporates. If you open a gas can in a closed area, all of a sudden you smell gas. If you can smell it, if you can smell a molecule, if you can smell a substance, some of that substance is in your nose, right? There's not any kind of magic. You're not doing ESP and ESP. I was going to say ESPN. You're not doing ESP on. I was going to do it again. You're not doing ESP on the substance, right? That substance is in your nose. So the more volatile something is, the easier it is to smell. Hexane comes in at about 68. It's a liquid. You'll see it in lab. 68 C is above body temperature. What is body temperature in C?
25?
Huh?
25?
25 is room temperature, give or
Oh,
take.
well, there's
37. Who said that? Are you European? Good. So I don't know where you guys will land. I grew up in Oklahoma, very anti-metric state. And so now in my head, at work, as a professional scientist, everything is metric. I step out of the lab, no idea. I have real trouble converting Fahrenheit to, everything is Fahrenheit in the real world. In the lab, it's all C. So when I live abroad, the oven is set to Celsius. Like I crank that thing up and nearly burn the place down. So anyway, boiling point of hexane is about 68. What's the boiling point of water?
100.
Yeah, there's one you should know. Look, what is the molecular weight of water?
18.
Right, so molecular weight, you just, atomic weight of all the atoms summed up. Oxygen 16, 2 hydrogens at 1 apiece, that's 18. So what's the, you guys probably saw this then on the video, what's the, so how many, what is the volume of a mole of water?
18 milliliters.
18 milliliters. The density of water is 1. In organic chemistry, the density of water is 1. In general chemistry, physical chemistry, it's like 1.00, and there's some digits out in the 4th and 5th place, and it varies with temperature. It's way too much work for an organic chemist, all right? It's 1. Round to 1. So 18 mils of water contains 6 point something times 10 to the 23rd molecules of water. A really important lesson as we start to talk about the language of chemistry, you are almost never going to deal with a molecule. Right, so I wrote this chemical reaction here. Hydroxide plus H3O plus goes to 2 waters. That does happen on a molecular scale. These molecules are real, honest to goodness objects. All right? But you never do a reaction where you have 1 molecule of this and 1 molecule of this, and it makes 2 of these other things. Right? It's always a whole buttload of this one, maybe a lesser amount of this one, and you get a ton of this other stuff. Right? So you always have all these molecules floating around together. That's why I try to start with water. This molecule is not this symbol. This is a symbol that lets us talk about whatever this is. This molecule is probably a white solid, like the aspirin you're going to work with today. How many people have had labs so far? Cool. All right, so back over here to me talking about water. Water has a molecular weight of 18, and it boils at 100. It's a small molecule. Hexane boils at 68. What's the molecular weight of hexane?
90?
90-ish? I like the way you think. So what is it? 6 times 12
Plus like 18
plus C6H2N plus 2, 12, 14.
Oh, 14.
So 72 and 14, 86.
Cool.
I wasn't going to get there. The molecular weight of hexane is a lot more than water. The physical size of hexane is a lot more than water. And yet the boiling point's lower. All right? The reason for that is the only interaction between hexane molecules is van der Waals forces, right? The only way 2 hexanes stick together is just sort of this induced dipole, weird attractive force between matter. So 2 hexanes, 2 alkanes, any 2 molecules have sort of this induced dipole van der Waals interaction that makes them stick together. And so then you have to think about what boiling physically means. Okay, so if I spill some gasoline on the ground, you shouldn't do this. It's not good for the environment. But if I do that, I'll smell it. Almost instantly. Right? If I spill gasoline on the ground, almost instantly, molecules in the gasoline are evaporating into the air, and I suck them into my nose. All right? So the gasoline molecules actually have to leave the liquid. So boiling is liquid turning into gas. You all know that intellectually. I want you as much as possible in this class and in the lab to think about real things. Okay? You've all done chemistry every day of your life. You haven't thought about it theoretically, but you have manipulated matter. You've taken matter into your body and converted it into energy. You've done this every day. So you can think about these real things. The 2 water molecules are more, the trillions of water molecules stick to each other with a hydrogen bond. Hydrogen bonds are really, really powerful intermolecular forces. Everybody good with that? So, to dissolve a molecule, we've got some molecule X. Does it dissolve? What you have to picture is you're going to insert X between the two waters. Right? So that's really what happens. If a molecule dissolves in a solvent, that molecule, the solute, the thing that's dissolving, has to end up inserting itself between molecules. For that to happen, the only way that happens is X needs to be able to interact with the solvent molecules. Right? So with water, primarily, everybody always talks about polarity. Polarity is important, and water is a pretty decent solvent for ions. It's better than hexane. I don't like this math, sorry. All right, so water is a good solvent for polar, but beyond polar, think about what kind of polarity. So really, if X hydrogen bonds, good chance it'll be soluble in water. If it doesn't, so let's say, is hexane soluble in water? Anybody got a guess? Hexane going to be soluble in water? Is gasoline soluble in water? Nope. Anybody ever mix like vegetable oil in water at home? Are those soluble? Cool. So hexane's not going to be soluble in water because it doesn't interact. You've taken two things that hydrogen bond together, and you've interrupted the hydrogen bond for van der Waals. Water doesn't do much van der Waals, right? It's this really small, tiny molecule. What did I just draw? Yeah, that's too, we'll give it that way. So, drawing a molecule here. What molecule is that?
Alcohol.
It is an alcohol. All right, so on most of the planet, if you say the word alcohol, they will give you that molecule. So you're not technically wrong. Well, you're not practically wrong. All right, if I walk over to the quad and I say, anybody got some alcohol? That's what I'll get. And fire. So, this is ethanol, 2 carbons, right? CH4 is methane. CH3 is ethane. If I take one of those H's off and I replace that H with an OH, I get ethyl alcohol. And again, you guys have a pretty, everybody has pretty equal experience with water. You guys probably have a little bit varied experience with alcohol at this point. But methanol, so in a chemistry